Okay, so today's topic, image enhancement, is mainly deals with improving the sharpness of the image. And for that, we have, similar to what we had for image smoothing, the kernels that were there, the convolution kernels, that is the 3 by 3 matrix. Same thing we have in this case. Now, I think I'd shown you all the Gaussian, no, I'd shown you all the Gaussian kernel, right? So before we go to exactly calculating the basically the sharpening part, we have to know what do we mean by gradient. Now, when I say gradient, it is basically the difference between two adjacent pixels. What is the intensity levels, and that gives you the difference between the intensity level, gives you the magnitude of the gradient. Now, gradient is actually a vector, and the direction of this vector is given by the direction in which the intensity level is increasing. Now, this gradient vector will always point to the it will always point in the direction where the intensity level is increasing. So, for example, if I have just a minute, just a minute, students. I will show you exactly what that gradient is. That is this. Okay. So, if I have an image wherein the intensity level is changing across certain pixels in a certain direction, then this gradient vector will always point in the direction of increasing intensity level. Okay. Now, in this case, it is just the opposite. When that is in this particular image, it is showing it in the opposite direction. Okay. That is white should be over here, and as we go away from the center, it should be black. But in this, it is just the opposite. I don't know why they mentioned it like this. Okay, so your gradient vector will always be pointing towards the brightest pixel nearest to it, whichever is the brightest pixel, and you'll be calculating this gradient at every pixel. Okay, now depending on the computational this thing value, how do we calculate this magnitude? Because this is just if it is a vector, normally when we have vectors, we want to calculate the magnitude of the vector. We have different forms of this calculation. The most prominent is the Euclidean distance, which is basically the sum of the square root of the sum of squares. Okay, if you remember the Euclidean formula, if I have a vector with components x and y, that is, if this is a vector v with x and y as the components, then the magnitude of this vector v is given by square root of x square plus y square. Okay, this gives us the total length of this vector. Okay, now similar to this, we basically have this divided into something called as the L0 norm, the L1 norm, and the L2 norm. Now, this L2 norm is your Euclidean distance, which is given by this formula over here. Okay. Now, the L0 norm basically considers that it is either zero or non-zero value. That is, if it matches what we are looking for, then we get the output as 1. Otherwise, a higher value depending on how many values are matching. And if it doesn't match, we get a 0. Okay, so this norm doesn't actually work well with calculating of the gradient, so we also prefer the second one. So this is just a 0 or a non-zero value, so we don't use this in calculation of vectors, the magnitude of vectors. This is usually used in cases of comparing your username password vector. Okay, so if you have a vector wherein you're storing username and passwords together, in such a case, if you're matching this, then if it completely matches, then you can say that the output is 0, and therefore you can successfully log it. If any of these don't match, if just the username doesn't match or the password doesn't match, your output will be 1. If both are not matching, that is, you haven't entered the correct username, neither have you entered the correct password, in that case you will get output as 2. Okay, so this number of mismatches, that is what counted in L0 norm. L1 norm is also called as the Manhattan distance, or called as the taxi cab distance. Okay, so the reason it is so called, because if I have, let's say, a grid. Now if you have seen aerial images of New York City, the way the streets are, it is in a grid format. The architectural layout is called as an iron grid or something like that, it is called. Okay, so if these are the roads, then these also form the roads. Okay, horizontal, and in between this space you have your buildings. The same thing you can say is near in Panjim, where we have the 18th June road. Some area of that, they have that parallel roads and intersecting roads, something like this. Okay, a small portion of that, but in some major cities you have all the roads connecting, something like this. So let's say in this case, if you were to take a car from this point over here, which is your starting point, to this point as your destination, now either you could take the route as this, that is, you can either go straight like this and then go up, or you can do this other way, or you can take a zigzag way, that is something like this. So you start here, go here, 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 and so on. Okay, so since there is no path in between to cut through, we make use of the streets which are already existing. That is why it is called as the Manhattan distance or the taxi cab distance, because of the Manhattan this thing, exactly how you would have to traverse it. Okay, now this Euclidean norm is what gives us the precise value, okay, about the distance. Well, the shortest distance, if you remember, there's that this thing, the shortest distance between two paths is a straight line, and if I want to calculate what is this distance, I can get that from the Pythagoras theorem. So if I have this distance and this distance is known, I can calculate this as the square root of the sum of squares of these sides. Okay, it was called as the Euclidean distance. Now, the problem with using Euclidean distance is twofold. One is, even though it gives us the accurate value, the problem arises in the calculation of this square root. Now, already we have to calculate the squares, so we are increasing the complexity in terms of that. Okay, so we have that multiplication operation coming into the picture, plus square root, it doesn't, the way in which computers calculate square root hasn't reached that level of accuracy yet. Okay, if you did you all have a subject wherein you had something like approximating what would be the value of integral or some derivatives based on basically how you would have to calculate on a computer if you were to approximate your continuous functions, operations which work on continuous functions with discrete values. Have you all come across that? Because we, when I was in my BE, that time we had a subject, numerical methods. In another subject with the same subject had a different name, as computer oriented numerical techniques or something like that. So it was basically like if I had to make some calculus operations or something related to these operations which were not feasible to work with because of the discrete data, we had to approximate it. Okay, so with square root also the same thing happens. We cannot find out the exact value, and therefore we have to find out an approximate value of the square root. So that is where this problem arises, wherein we cannot, first of all, we cannot get the accurate square root value, and second of all, we also have to calculate the square. So these combination is what we is the reason why these combination of these methods is the reason why we prefer to use the L1 method, which is just the sum of these distances. So if I were to travel from S to D, and let's say this distance is 5 units and this distance is 4 units, then this total distance approximately is 9 units. Okay, the sum of the individual components. Okay, so instead of taking it as square root of x square plus y square, we take it as sum of x plus y as the approximate distance. Okay, so this approximation of this gradient vector in calculation of magnitude, we use the L1 method, also called as the Manhattan distance. Okay, now we basically have four major ways in which we can calculate the gradient. So this is basically the gradient. So if you can see over here, that is these are the brightest. Okay, so if you check the similar corresponding point over here, that is in this image, this image, this image, and here, there is a sharp difference between the intensity of this brake lever with the background. So the edge between this background and this brake lever, there is a sharp change in intensity. So that is what is highlighted in this gradient calculation. Okay, so gradient is usually a term which is used for not exactly gradient vector, but if this pattern, as you go near or away from certain points, the intensity changes gradually. Okay, so if it is a gradual change, we call it as a gradient. But what happens is, if it is a sharp change, then we call it as an edge. Okay, edge in that particular the changes in that intensity value. Okay, so these operators, even though we do get gradients, which is basically the difference, if there is an edge, something like this, okay, then this change is going to be very high. The difference between these intensity value over here, I'll use a magnifier just in case, so that you all can also see properly. Okay, so let me increase it further. Okay, so if this part, this black lever, okay, all the components within this black lever, if you see over here, they are going to be having the same intensity. So since we are calculating the difference between these intensity values in the corresponding neighboring pixels, if the intensity values are very similar, then we consider it as a very low difference. So when we plot it as gray level intensity, this difference values as gray level intensities, then higher the difference, brighter that pixel will be. Okay, so that is the reason why you will find that if it is a sharp edge between different intensity values, at that time, that line which separates these both intensity values, that will be brightest. That is what we call as an edge in this particular pixel, in this image. Okay, and that is what we get in these Roberts operator, Privet operator, and Sobel operator. Now the Roberts operator, the convolution matrix, it comes something like this. Lakshmi, your camera is on, just notifying you. So the Roberts operator, okay, sorry, where did I get the, okay. So the Roberts operator has a matrix as 0, sorry, not 0 over there, that will be y. Should not have selected that auto hide. Okay, 1 0 0 minus 1 and 0 minus 1 1 0. If it is 1 1 1 0 0 0 minus 1 minus 1 minus 1, and this is 1 1 1 0 0 0 minus 1 minus 1 minus 1, and Sobel is 1 2 1 0 0 0 minus 1 minus 2 minus 1 and 1 2 1 0 0 0 minus 1 minus 2 minus 1. Now you must be wondering why we have two convolution matrices when in earlier in smoothing we just had one convolution matrix. Now this is because the gradient when we want to calculate, since it is a vector and this is a two-dimensional image, the vector itself will be a two-dimensional object, okay, two-dimensional entity. So this calculation will have to be done in terms of two dimensions. This is your x component and this is your y component. Similarly, your Privet, this is your x and this is your y, and Sobel, this is your x and this is your y. Okay, I think I wrote it the other way around. No, it's correct. So here the only thing you'll have to consider is that when I say x, it will be the rows. Okay, so these are your rows. That is, this is the first row, this part is your first row, this part is your second row, third row, and so on. So that is the reason why we consider x as this direction, vertical direction, and y as horizontal direction. Okay, now it won't make a difference in terms of the magnitude of the gradient vector, but you can interchange this. Okay, but make sure that you don't use both of them as same, because finally when we are calculating this gradient, the intensity value, that time we just have to add whatever is the sum of the x component and the sum with this value of y component. So the magnitude of the vector will be whatever is the convolution of this image with x plus convolution with y, and the sum of these two components we add together because that is your Manhattan distance, L1 norm. Okay, so we add these two components and that becomes the intensity level of this pixel. Okay, now regarding this, we'll solve numericals in class in next week so that you all don't have any doubts with this. Okay, we have another one called as the Laplacian operator, or also called as the Laplacian edge detection algorithm, which basically uses this convolution matrix. Now the reason it is called as second order derivative is because your earlier ones, all of these three, they just calculate the difference between the current pixel and the next pixel. Okay, and if you remember when you studied calculus, your derivatives, that time you must be remembering that derivative basically gives you the rate of change of the value. Okay, so that is what we are doing over here. The gradient, the direction and the magnitude of this gradient, the direction will give you the direction of this change, which direction it is changing, and the higher the gradient value, that means the higher the rate at which the intensity level changes. Okay, so in a Laplacian gradient operator, we don't just take the first derivative, we take the second order derivative of this image. Okay, now I'll show this derivation in class itself. It's a very simple derivation, you don't have to worry about it. Okay, it just states that it is the second order derivative. So when you're approximating the first order derivative, you have to take the difference between two pixels, and the difference between these two pixels, that is the gradient of these two pixels, again you have to take the derivative. So what you get is this equation. So your x will come this way, that is in the x direction, your convolution kernel will be in this equation, and your y convolution kernel will be this. So this part basically becomes as -2. So these two separate components are there, 1, 1 and -2. And in y component, in x component, you have 1, -2 and 1. So when you add these two together to find out what is the magnitude of this, you get this kernel 0 1 0 1 minus 4 1 0 1 0. Okay, we'll solve this derivation in class. Then we have the corresponding frequency filtering, which is if I want to apply edge detection on that image, I can convert this image into the frequency domain and then apply high pass filtering. So the same thing comes over here also, that is in the ideal high pass filter, we are only allowing the higher frequencies to pass and the lower frequencies to, they are blocked. So again the same problem arises as with ideal low pass filters, that is your ringing effect, those lines that are shown here over here. Okay, so when I apply ideal filters to this ideal pass, either low pass or high pass, we have these lines coming up which forms like that object is ringing. That is why it is termed as ringing effect. Okay, you can just Google about it, ringing effect with filters. You will get the exact reason why that comes. Okay, then comes your trapezoidal filters, which are basically this edge becomes instead of just cutting off, you are slowly decreasing it, so it becomes a line. And finally Butterworth filter, which is like the flipped version of Butterworth low pass filter. Okay, the equation, just the polarity changes, the minus sign comes into picture, that's it. Okay, we'll see each of these equations in class also. Now you will never get an numerical for with frequency based filtering in the frequency domain, because you will have to convert the image into the frequency domain and then apply filtering to that. So any numerical you get with either image enhancement or with image smoothing, that will be based on these operators, and it will always be in the spatial domain. Okay. And another topic is your image restoration. What we'll do is, there's only 10 minutes left, so the image restoration is a bit complex topic, and we have this image processing model used as image degradation model also, and then we have these two equations which have to be derived. Okay, so there are two derivations with this, that is your unconstrained and constrained, which uses the Lagrange multiplier method. So we have a slightly long derivation with that. It's not very long as such, about 5 or 6 steps are there, but you have to be careful in the steps. So I'll try to get this done in the classroom, the physical classroom, so that we don't have any doubts in this. Inverse filtering is pretty easy. We just take the idea of the image processing model with noise, convert it into the frequency domain, and then try to find out what would be this noise constraint. Okay, so we try to approximate what this MUV would be, and then we try to apply inverse operation to that so that it cancels out. That is the idea. And Wiener filtering, again, similar thing. This is what I want to focus on in the classroom. That is not this lecture, the lecture after that. So this is what I was saying, and this is an example of geometric errors or geometric aberration. So when we have something like a wide angle image, especially on the edges, instead of these lines being straight, because obviously buildings are not going to be curved like that, these curving is coming because of the issues with the lens. Okay, so the problem actually arises because this problem will be there in every every wide angle lens. The only difference is how prominent it comes in terms of these corner pixels. Okay, this corner light, there's some term for it. You can check online why these curving effect comes. Okay, so what we try to do is we try to find out how exactly we can remove that, and especially right, fisheye. That term fisheye is there, but fisheye is much more prominent than just this. Fisheye completely changes the way that image looks, wherein you have completely rounded kind of thing. Let me just try to find an image where you get, yeah, so something like this, wherein the object itself is in a curved manner. But the reason fisheye lenses are used is because it covers a lot of area. Okay, you get a much wider angle. But this is called as fisheye. Okay, it just has to be more prominent, then it is considered as fisheye. So what we'll do is we basically have to remap these objects which are there in one image with another image. Okay, and then we try to find out exactly where it will lie. Okay, so this is specifically required when we have some, especially with satellite images, and so we try to remove these geometric errors. Okay, so we overlap this earlier image with this. Now you must have seen one example of geometric aberration in terms of when you were uploading your papers last year, IT papers. When you are uploading, the edges of this papers would, if they were not on a flat surface, the it wouldn't come as a flat image, and then the text would come slightly bent and so on. Okay, so we will be finding out exactly how we can do this part, that is how we can remove geometric aberration in terms of remapping the pixel locations. Okay, this I will try to do this in class. It's mainly theory, but there is some equations also required. So that is the reason why I want to do this part as well as these in class. So I'll see you all on Tuesday in lecture. So that time we'll see this. That's it for today. Thank you. Yeah, basically we will have that non-rectilinear. Right. It is correct. It's supposed to be linear, but then it doesn't come as linear. That is what is called a non-rectilinear. Correct.